Welcome back, everyone. This is Dr. Minitab-Tamayo-Kieke once again. This lecture video is the second under Unit 1-2, Inferential Statistics. In the previous video, we discussed the general procedure for hypothesis testing along with some examples. In this lecture, we're going to continue our discussion on hypothesis testing, and specifically by the end of this lecture, you're expected to achieve the following. First, to understand and apply the p-value approach. Second, to determine confidence intervals. Third, to perform assumption checking. Fourth, understand the importance of sample size choice. And fifth, understand and solve other hypothesis testing cases. However, as usual, before we start with this lecture's topics, let's first have a review question. And I encourage all of you to pause the video first before you proceed with the succeeding slides and make sure that you're able to understand our review question. This is very simple, actually. Okay, so here goes. Suppose we have a null hypothesis, H0, mu1 is equal to mu2. What is the alternative hypothesis H1 represented by each of the following figures? Is this a one or two-tailed test? Okay, so the leftmost figure represents an alternative hypothesis testing mu1 is not equal to mu2, which is a two-tailed test. The middle picture is mu1 is greater than mu2, which is a one-tailed test. And the last picture is also a one-tailed test where our alternative hypothesis is mu1 is less than mu2. And as you can see represented here, you have your critical regions. And what is the critical region again? Okay, so also make sure that you are able to answer that question before you proceed to the succeeding slides. Now let us start our discussion on the p-value approach. And this is in contrast with the fixed significance level testing. Now recall that in fixed significance level testing, we are primarily concerned with the question: at a specified level of alpha, was H0 rejected or not? Okay, there are some problems with this approach. First, the user has a vague idea of how far the test statistic is into the critical region. And secondly, some might not be comfortable with the risk implied by a predetermined alpha. So we resort to the p-value approach, where the p-value approach is concerned with the probability that the test statistic will take on a value that is at least as extreme as the observed value of the statistic when the null hypothesis H0 is true. Now let's go back again to our Portland example. In this experiment, the engineer wanted to determine the impact of adding a polymer latex emulsion during mixing to tension bond strength or of the mortar. The original and the new formulations are the levels of the factor, which is tension bond strength. In this slide, you can see Minitab t-test results for our Portland cement example. So this is a sample output from a computer run using Minitab for our Portland cement experiment. And as you can see encircled here is the p-value for this test, where the value is equal to 0.042. What do you think does this mean? Well, if you go back to the definition by Montgomery of the p-value, it's actually the probability that the test will take on a value that is at least as extreme as the observed value of the statistic when the null hypothesis H0 is true. Okay? Again, the p-value gives you the probability that you will get a value for your test statistic that you got from your sample data, assuming that your null hypothesis is true. So the p-value essentially gives you the likelihood that your sample data actually supports your null hypothesis. So for example, suppose that a vaccine study produced a p-value of 0.03. This p-value indicates that if the vaccine had no effect, you'd obtain the observed difference or more, or a more extreme case, in 3% of the studies due to random sampling error. So your p-value actually answers one question, and that is, how likely are your data assuming a true null hypothesis? So it actually does not give you a measure to support the alternative hypothesis. It also is not equivalent to your type 1 error. Okay, and of course, one of the reasons for this is that by definition, type 1 error is the error of rejecting a true null hypothesis. In the p-value, you are actually assuming that your null hypothesis is true. Okay, so you're simply asking whether your data actually provides you enough support, okay, or enough evidence that you can reject or accept your null hypothesis for the entire population. And of course, a low p-value suggests that your sample provides enough evidence that you can reject the null hypothesis for the entire population. Why? Because a low p-value translated into words means that there is a low probability that you will be observing the values that you got from your sample data in the actual population if your null hypothesis is true. So in our Portland cement example, given our Minitab results, our p-value is 0.042. Again, what does 0.042 mean? It means that, assuming that our null hypothesis is true, and remember that our null hypothesis is that the mean tension bond strength of the unmodified formulation is just equal to that of the modified formulation, meaning their difference is equal to 0. Okay? So the p-value of 0.042 means that you will observe the values that you observed in your sample data, given that the null hypothesis that there is no difference between the modified and unmodified formulations is true. Okay, so since this p-value is so small, it indicates that your data does not support, okay, or does not manifest the trueness of the null hypothesis. Therefore, you could conclude, maybe if an acceptable probability for you is 5%, okay, then you could conclude that you want to reject the null hypothesis in this case. Now let's move on to confidence intervals. When we want to determine the confidence interval, what we actually want to get is the range of values L to U, such that the probability of obtaining a value of the parameter theta that is between L and U is equal to 1 minus alpha, where alpha here is our significance level, or the probability of rejecting a true null hypothesis. Now in a two-tailed t-test, our parameter, theta, is transformed to this term here. Okay. And this is actually our test statistic. Okay. Since we have a t distribution and we want the probability of 1 minus alpha, that our test statistic will fall within the confidence interval, then our confidence interval will consist of a range with the lower limit that would simply be at negative t alpha over 2 with a degrees of freedom n1 plus n2 minus 2, and an upper limit of t sub alpha over 2 with a degree of freedom n1 plus n2 minus 2. We can further transform this to get the confidence interval for the difference between the population means, as shown here. So now this will help us, okay, from the previous slide. So this term here, okay, will now help us to determine the confidence interval for the difference of the two means, where the limit, the lower limit, is this term here, and the upper limit is this term here. Okay. From our Portland cement example, you can now calculate the values for each of the terms here. You can calculate, for example, the mean for the first, for the modified formulation, and the mean for the unmodified formulation. According to our Minitab results, it's 16.764 and 17.042 respectively, but of course you can calculate this using your calculator or manually, or other softwares that you have or you prefer. And then of course you have your pooled standard deviation, okay, and that would be 0.2843. And then from your t-table or using your Excel or R or other softwares, you can get your t values, okay. So plugging in all those values, we get the confidence interval to be negative 0.55 to negative 0.01. And this is actually reflected in our Minitab results here. And as shown, this is the confidence interval for the difference of the two means. Alright, so given our Minitab results, given this confidence interval, what can you conclude? Do you accept or reject the null hypothesis? Before we answer that, okay, I'd just like to note that, of course, you can also run the test in free software such as R. Okay, and the code is actually fairly simple over here. Okay, and you get the same results basically. Okay, so given our confidence interval. Oh, by the way, as you can note, the values are slightly different because of the assumptions that are used in the two softwares. In the R, the Welch 2 sample t-test is used. Okay, so let's base our conclusion on, but the conclusions from the two results are basically the same. Okay, so given this confidence interval, what would be your conclusion? Recall that our H naught is that mu1 is equal to mu2. In other words, the difference between mu1 and mu2 is equal to 0. Or mu1 minus mu2 is equal to 0. So, is 0 included in this interval? Obviously not. Therefore, we reject the null hypothesis. And this confidence interval indicates that the difference is negative, meaning the the mean of the second population is higher than that of the first. So in our case, the mean tension bond strength of the unmodified formulation is actually higher than that of the modified formulation, which is, of course, not to our liking. Before we proceed, I'd like you to do a concept check. Okay, so make sure that before you continue with the rest of the lecture, that you actually understand the concept of the p-value and the p-value approach, and then the confidence interval and how to determine it, the normality assumption, recall from the previous topics, and the independence assumption. Okay, so let's go back to the discussion of the normal probability plot, which is a very useful tool in checking or verifying the normality assumption. A normal probability plot, as shown here, shows the sample quantiles on the y-axis plotted against the theoretical quantiles on the x-axis. Now, on your own, if you don't know yet, find out how a normal probability plot is made. Of course, you can generate the normal probability plots using your preferred statistical software such as Minitab or R. Now, how do you use the normal probability plot? It's fairly simple, actually. The test is called the fat pencil test. In this test, you imagine that you overlay a fat pencil across the points. Now, if the points fall within that fat pencil, then the data passes the normality test. For our Portland cement example, this is the normal QQ plot of the modified formulation, while this is for the unmodified formulation. As you can see, both appear to pass the fat pencil test, okay, or the points fall approximately in a straight line. So there are other things that we can observe just by looking at these normal probability plots. The second one is, okay, so from the first one, because the points fall approximately in a straight line and pass the fat pencil test, then we can conclude that the normality assumption is appropriate. And as you can also see, the slopes seem to be similar. And this indicates that the two samples have equal variance, or the assumption that they have equal variance is reasonable. Now, what if the fat pencil test is not satisfied? What does it mean? The performance of the test, meaning the statistical tests that you make, will be affected if the assumptions are not satisfied. One specific repercussion is that the significance level and ability to detect differences between the means can be affected. So there are some approaches that you can resort to, such as transformation of the data and non-parametric tests, if the normality assumptions and the independence assumptions are not met. This will be discussed later in the course. We need to always remember that the choice of sample size is one of the most important parts of an experimental design problem. Let us consider the effect of n on the estimate of the difference in two means. Previously, we determined the confidence interval of the difference between two means, that of the modified mortar mix and the unmodified mortar mix. To do this, we use this formula. The 100 times 1 minus alpha % confidence interval determines the precision of the estimation. And from the formula, you can see that the length of the interval is determined by these terms. Now, let's first consider the case where we have equal sample size from the two populations, so N1 equals N2. In this case, the length of our confidence interval is determined by this formula because we don't have control over the pooled standard deviation SP. So now, if we plot this versus n at alpha equals 0.05, this is what our graph would look like. Increasing n increases the cost of experiment. Now, as you can see, as we go beyond 10, the change in y is marginal. That is, the change in precision is small. We want to choose the smallest n possible without sacrificing precision, of course. So we can say, based on this graph, a sample size of 10 to 12 would be enough to have a confidence interval with the best precision of estimation for the difference of the means. We can also use operating characteristic curves to determine an appropriate sample size. This is a graph of beta versus delta, where delta is the difference between the means divided by the standard deviation. The beta error is a function of sample size, and in general, as sample size increases, beta error decreases. This means that the difference between means is easier to detect when we have larger sample sizes. Alternatively, we can use the power curve, which is the graph of the power, which is 1 minus beta, versus the sample size as shown here. This is an example of a power curve. This is generated for testing the difference between two means where the variances are unknown but are assumed to be equal. The sample sizes are also assumed to be equal, and the sample size n on the x-axis is the sum of the two sample sizes, n1 and n2. We assume a significance level of alpha equals 0.05. Now also note that the difference of the two means are expressed as a ratio to the common standard deviation, sigma. This ratio, delta, is higher when either the numerator is higher, that is the difference between the means is bigger, or when the standard deviation is low. So, what can we say from this graph? We have curves for cases with three different deltas. Delta equals 1, 1.5, and 2. Okay, the first one is the greater the difference between the two means, the higher the power. That is, we have a smaller type 2 error. This means that for a given sample size and significance level, it is easier to detect larger differences in means, as you can see here. The next observation that we can make from this graph is that for a given difference in mean significance level, the larger the sample size, the higher the power. As you can see, if you just look at this curve here, okay? As we increase the sample size, we increase the power. This means that to have a more powerful test, we need a larger sample size. Now let's take this as an example, which is still connected to our Portland cement experiment. Suppose that in the Portland cement experiment that we discussed previously, a difference in mean strength of 0.5 kgf per square centimeter has practical impact on the use of the mortar. So if the difference in means is at least 0.5, we would like to detect this with a high probability. So, because this is important, this is a critical difference in means that we wish to detect, we find that the power curve parameter would be delta equals 0.5 divided by sigma. We don't know the sigma here, the population mean, but suppose that based on past experience, it is very unlikely that the standard deviation will exceed 0.25. So just suppose that for the sake of this example. Then substituting 0.25 to our formula to get delta, we get 0.5 divided by 0.25 equals 2. Okay, so then we use this graph. Okay, thus if we want to reject the null hypothesis when the difference in means mu1 minus mu2 equals 0.5 with probability at least 0.95 or power equals 0.95 with alpha significance level equals 0.05, then based on this curve here, okay, we find that we need a total sample size of 16. And since n is actually the total of the two sample sizes, and we know that n1 equals n2, then n1 and n2 is equal to 8. Okay, I will stop the lecture video at this point because it is getting too long. We will continue our discussion on other cases for hypothesis testing in the succeeding video. Bye for now.